Hi everyone, welcome to this video. I'm going to introduce our review paper for microscopy 70th anniversary issue on data-driven electron microscopy. Specifically, we focus on electron diffraction imaging of materials structure properties. I'm Jian-Min Zuo. I'm from University of Illinois. The idea of data-driven electron microscopy is based on two major developments of transmission electron microscopy. One is the continual improvement in electron optics that led to the atomic resolution imaging, and the same improvements also led to the development of illumination system that can be used from probes anywhere from sub-angstrom to nanometer or hundreds of nanometer in size. The second development is in pixelated electron detectors, and starting from early 1990s, the development through scan CCD camera for electron microscopy led to the digital revolution, which replaced the photographic films for electron image or diffraction pattern recording. The digitized format enabled quantitative analysis of both electron diffraction patterns and the electron images, and also improves the detector quantum efficiency. More recent development is direct electron detection, and this has led to the revolution of cryogenic electron microscopy, and also enables high-speed readout with a large dynamic range for collecting many diffraction patterns in a short period of time. The idea of data-driven electron microscopy is to connect large diffraction datasets using scanning electron nanodiffraction, or popularly known as 4D STEM. The idea is to form a small electron probe and rest this probe across a region of interest on the sample. By recording diffraction pattern at every beam position, we collect a large diffraction datasets, and those datasets can be processed from image for quantification. There are different forms of scanning electron nanodiffraction or 4D STEM, depends on how the beam set it up. The common theme of this technique is a large data size. For example, if we do a 512 by 512 pixel scan, this produces roughly about 1 terabytes data, and that's automation for data analysis is critical. This slide summarizes the basic idea of data-driven electron microscopy, and by collecting a large data cube where xy is the diffraction coordinates and the s is the number of diffraction patterns being captured, using different techniques which is shown here, we can use computer processing, including indexing, refinement, dynamic inversion, and tomography, and also recently introduced separature transformation for the study of disordered crystals. We can also introduce the advances in data science, including artificial intelligence and machine learning. By processing, we extract crystallographic information and use that for imaging, and this significantly expands the capability of transmission electron microscopy. In our paper, we reviewed several major applications of data-driven electron microscopy, including diffraction tomography, which determines the grain orientation as well as the grain morphology, and the imaging of the defects in molecular crystals, and orientation mapping for nanostructured thin films, and also for study of single crystals by looking at the local symmetry due to the presence of defects, for example, and look at the strain mapping. So you're welcome to read our review paper. I thank you for your attention.